Hi, love. No, I've postponed it a little bit. It's a sweet-looking house. It's I think it's very good. It's astonishing value. I mean, in terms of comparison to getting that much space and what I assume is a decent quality house. I didn't look at the inspection report, but I mean, yeah, corner lot. It looks as though it's protected by existing houses from, I'm not sure what, I think the green space to the east is a park, so that looks protected. The developments that they're talking about in Picton seem to be around the harbor primarily. And I think new development, I mean, it's just going to add to the population. Therefore, the services will improve and property values will go up. So I'd say it looks pretty good. Well, it will. It will. It's. I mean, having seen, I dated Lynn Bevan, who lived in Kleinburg back in the 70s, and
Hello.
more and more subdivisions went up around Kleinburg, and eventually the old village became kind of a bijou little, hotspot. So people would flood in on the weekends and so forth, so that the character of the village eventually morphs into something, a bit more Disney-like. So no, her family sold, I don't know when, but I last time I was up there, I drove by. They had the old schoolhouse on one of the back streets. And
sir, I don't know if you can hear me, but your mic is unmuted.
Oh, sorry. Apparently, I've left my mic on. Okay. Okay, love. Okay. Thanks. All right. Bye. Hi, gang. You've been listening into my conversation, have you?
We tried telling you.
I was talking to my daughter, and the woman that she shares an apartment with at the moment in Toronto is just considering buying a house in Picton. I don't know if you know where that is, but it's down in Prince Edward County, which is that big peninsula that sticks into Lake Ontario, sort of halfway along the North Shore there. So that's what that was about. They were asking my opinion on what was happening to the village and town and house, etc. So now you know. That's what was keeping me. So good morning, everybody. How's the so I've had an email or two about some groups that are not working. I'm sorry to hear that. I haven't had a chance to dig into it yet, but let's spend some time on that this morning. I also want to look at your proposals, which again I haven't had a chance to look at, and but I will do shortly. So anything urgent on your minds at the moment, and or something you'd like to add to the agenda?
I saw someone ask in chat if everybody needs to submit or just one per group.
Oh, just one per group. Just make sure that the submission has everybody's name on it, which I showed you in the sample I gave you, right? It has everybody's name and their student numbers. Yeah.
Professor,
Yes.
in my group, we're 5 in my group, but 3 of them haven't shown up. So I wasn't able to get the student numbers. Only 2 of us. I'm a little worried that it's going to be left to just 2 of us to do the whole project as well.
Okay. So did you add their names but not their student numbers to the?
Yes.
Okay. And did you also make a note of the fact that you haven't been able to get hold of those? You sent me an email about it?
No, I was going to. I just decided against it in case like they were able to show up later, because this aspect wasn't too like time consuming. But then when we start the real project, it'd be important to have the rest of the group available.
No, for sure that's important. And so try and make contact with them, and if you haven't succeeded by Friday, then we'll have to figure out what's going on. I don't know if they're out of the country or who knows what. Okay.
Yeah.
Anybody else having that same problem? Group members not responding. I did get one email from somebody, and I just had a quick glance at it, but I didn't take in all the detail. That somebody had trouble with their group. So, as I say, anybody here at the moment? I see we've got 55 people present, which is good. Is anybody here from section 101? No? Okay. All right. So as I said, we're going to cover steel early because of the project and because of hopefully it fitting into design studio work. By the way, how far along are you now with the design studio? What are you working on?
We're still learning on Revit.
Still
Just
doing
like-
Revit, so you haven't really launched into the project at all, eh?
No.
Okay. All right. Well, we will circle back if you haven't started until, we'll cover steel this week and next week, and then move on to something else. But if we need to come back to it, has anybody put up any material for a practice session tomorrow? Technical stuff that you want to have more information about, or details, or whatever. Maybe you're not far enough along to make use of that. Yeah.
No, not yet. I don't think so.
Okay.
I think next week might be the last Revit class, I think, and then we go on to side stuff.
I see.
So
Okay. All right. Well, let's talk about steel then. Now, how do I? Oh, I've got to upload a different. All right. So, structural steel. This is the architect's drawing of one of the bridges at Ashtonby campus. I don't know if you've been over there very much. Maybe you have some classes over there or something. And we'll see. We'll see how that goes. So there it is under construction. There's the structural steel of the bridges being installed. And what form of structure are we looking at? Trusses, correct. So we'll talk more about those as we go. Interesting, you can see, where some of the fastenings, the connections have been done in the shop. These ones here, and so that's why they are covered with gray primer paint. Some of the connections have to be made in the field, right? So on site, and so they have been welded, and that's why the primer is off, and they're starting to show a little bit of rust. So they'll come back later and touch up all the primer for all of the structure. Yeah. What am I? There we go. Okay, so what is steel? And we talk about ferrous. We'll talk about non-ferrous materials later in this course. Ferrous, the word comes from fer, or Latin for iron, and so steel is iron fundamentally, and then they add some carbon to it, and it's in the range of 1% to 2%, right? We know that iron can be used unalloyed, right? Cast iron or wrought iron, or, well, those are the two main types. Cast iron and wrought iron are used for a variety of different things. Certainly, when you think of garden fences and garden furniture, quite often it is made out of cast iron painted black. And there we are. So if it has more carbon, it is cast iron. I'm going to check those figures. Oh, here we go. So too much carbon, it makes the material less ductile, and so that's one of the drawbacks to cast iron, is that it's brittle. So somebody is saying they can't hear me. I don't know why. Everybody else can hear me okay? I just had a conversation with Bambasolo, so I guess must be your local problem. And to little carbon, we get a softer material, and it does allow it to be wrought. Does everybody know what the word wrought means, to wrought something? So imagine a blacksmith and somebody, shaping a horseshoe. They heat the horseshoe up, they heat the piece of iron up, and then they work it by banging it with, heavy hammers on a, what's that thing called that they work on? Anvil. That's right. So you use a hammer and anvil to shape the iron to the shape that you need. And you have to keep it hot in order to make it soft enough to work or to rot. And we'll talk later about the characteristic of iron. It doesn't burn, of course, but it is affected by heat and it softens. And we'll talk about how that affects steel a little bit later in this lecture. So steel framing, two little illustrations there on the right. We can see the skeleton of a steel frame. And I added a link, but it doesn't seem to be showing in this particular PDF, and I don't know why. Just give me a second. Anyway, I need to update your I'm just going to open this in another window and see if the link is active. Anyway, I've got to update this. There's some more sort of background reading you can do about what skeleton frame construction is, but fundamentally, that is the skeleton of the building, right? The bones of it. And so there we see the bones covered by cladding, by roofing, with the interiors in place and so forth, but we can still see the bones or the skeleton, namely the structural steel. So that is the basics of the structural system, and it is a framing construction, right? It's pieces of material that are joined together. They're typically long and thin, and so just like wood framing, we have steel framing, right? So they're strong, they are lightweight. I mean, obviously steel is heavy, but it's lighter than, say, concrete, right? So I think I showed you the project I worked on Bloor Street, where we put the building on top of another building, or an existing building, and we did it out of steel because the weight that we were adding, the total weight that we were adding that was eventually going to have to be carried by the foundations was obviously increasing by adding an additional 8 floors on the top of this existing building. So we did it in steel because it was the lighter structural material to use. And just a couple of examples of skeleton frame buildings. The Hancock Tower that we talked about last week because of the bracing question And I believe this is Foster's building, the bank in Hong Kong, right? Also steel. So we need to become a little bit familiar with how our structural engineers design these things, right? We talked about the fact that so we talked last week about how the structural engineers first figure out the horizontal structures, right? They start at the roof and work their way down to arrive at what the total load is, and then they do the vertical. So starting with the horizontal structure, if we Kirwan's question, yes, the PDF is on the eCentennial site at the moment. Okay. So this is the framing for a typical sort of office building floor size, and we can see that it's got a rectilinear shape, and it's got some special framing in the middle here for the core, right? So we've got elevator shafts accommodated here. The elevator lobbies would be here and here. And then we've got the typical floor bays out here, and they are pretty repetitive. You didn't find it on Centennial. Okay, hang on a second. Let me go back. Content. Oh, I see. It's this silly thing that they hide the default position when I create a new folder is that it's hidden from you. So I forget sometimes to open it up. Try now. Can you see it now? Good. Okay. So you got the PDF. And we'll talk in a minute about what these designations mean in terms of structural shapes. But fundamentally, the engineer will solve or will design a typical corner bay, a typical mid bay. The corner bay you see repeats, and then they've got some typical interior bays, and then that structural system will repeat around, right? Any questions on that?
Sorry, is that looking like down from above? Or?
Yes, this is a plan view. And as I said, what we're looking at is a typical floor. Oops, sorry. Come on. A typical floor. And this being an office building, it's got lots of elevators and shafts, for probably mechanical shaft here and here, and a total of 12 elevator shafts, right? 2 elevator lobbies, so the elevators are in banks of 3. And so this might be a lower floor because typically on the upper floor, these 6 elevators will stop at maybe the 20th floor, and these ones will carry on up to the top of the building. Yeah. So it's a plan view.
Okay, thanks.
Right. Okay, so having figured out the floor structures, then the engineers add them all up, and they start to work their way from the top down. And typically what they give us, maybe I'll do better to show you my PowerPoints here. Just a second. See if I can zoom in on that better. Well, it's really not that much better. So what this is known as is a column schedule. So the the engineers, when I zoom it, are you seeing the zoom?
Yeah, we are.
Okay. So I'm sorry it doesn't read very clearly, but you can sort of make out this is roof, right? And so what they do is they show the columns coming down the building in this kind of schematic form. And they make a notation about what the size of the columns have to be at different levels, right? So that they typically, the columns are getting bigger, stronger, heavier as they go down the building, yeah? They've got notes about where the splices, they've got tags to, so that the steel manufacturers, when they, or fabricators, I should say, when it comes out of the fabricator's shop and comes to the site, they've got tags attached to them. So obviously you want, just by looking at it, you may not be able to identify, one column may look much like another, but in fact, they've got different thicknesses and therefore greater strengths. And we need the stronger ones at the bottom. Yeah. And then base plate information is given so that again, on site, they know what size, shape, and connection is needed to connect the base plate of the column to the foundation. And so these forces are calculated, and then the engineers take it through. Typically, it's done with computers, computer analysis these days. In the old days, they did it by manual calculations and slide rules and things. And so they look at the horizontal loads that are coming onto the building due to wind and earthquake, and figure out how those are going to be, whether or not. So they first solve for simple gravity compression with the live loads and the dead loads in the building. And then they check whether or not the strength that they've got is sufficient for these additional loads, okay? And we remember that there's both upload and download on these connections right here, right? Because of the building being pushed one way or the other. Any questions on that? Okay. So steel, how do we get these shapes that we need, like this I-beams, a typical shape, and we'll talk about shapes in a minute. So we get the steel is coming out of the foundry, where it's been the carbon has been added to the iron, and it is rolled out into what they call ingots or billets. They can be round, they can be square, rectangular, they can be flat sheets, depending on what the need is at the end of the day. And then they are put through what they call rolling mills. And these rollers take the hot steel and deform it with huge amounts of pressure, right? Very hard steel rollers that are forced onto the hot iron, which is still hot enough to be shaped, and with successive passes through the rolling mills, they eventually arrive at the shape that they're looking for. And these shapes you're probably familiar with. Here's some of them. So the fundamental ones that we use a lot in building construction, the American Standard shape, which is what we commonly call an I-beam. These shapes here are called wide flange because they obviously they are wider on the top and bottom. The top and bottom sections are the flanges, and the vertical section is the web. So flange, flange, web. Yeah. We can produce channel sections, angle sections, T-sections, or just simple rods and rectangular solid steel members and flat plate. Yeah. And this is a kind of Bible. I certainly used it when I was in university and through my working days thus far. It's probably all digital now. I haven't checked recently, but it gives all kinds of properties that we'll talk about in a minute, which the structural engineers need to know when they're choosing what sections to use. There's a link here that will take you to, let me go over here to my slides. For some reason, it seems as though the links don't work in the so if I flip over to my I'm getting the spinning wheel. Can you see an orange cross-sectional shape on your screen?
Yeah.
Yeah. Okay. All right. So that's the link, and this is the these are the European standards, which of course are metric, and we're kind of a hybrid situation here in North America because of the American market. We typically work with imperial sizes, but they may be expressed in metric dimensions. Yeah, so you're probably familiar with that situation in other materials as well. So coming back to our framing diagram, or framing drawing, I should say. So the engineers say when they're designing the floor structure, they're taking into account live load, dead load, designing it for shear, designing it for bending, and they arrive at a shape that satisfies those needs. Yeah. And so they put them on their drawings, and then they send them over to us, the architects. And so we need to understand what it is they're telling us. Anybody know? Could anybody give me the information of what this being? So if I zoom in on the W27 by 102, what does that tell me? Anybody familiar with this system?
The depth of the flange.
Naomi's comment about span, yes, it's very critical for, I mean, they're designing it based on span, but span is basically the distance, right? So the structural engineers typically do not put those kind of dimensions on their drawings, right? They don't give a dimension from this column to this column. They know, having looked at the architectural drawings, that say for argument's sake, that's 30 feet, yeah? But because there could be conflict between the architects are the ones who are in charge of dimensioning the building, and therefore the structural engineers do not put dimensions on, yeah? They know that it could vary by a couple of inches or even as much as a foot or two because of what the architects are fine tuning as they get into their detailed drawings. So, but the engineer has designed it for this hypothetically we're saying it's 30 feet, and they've determined that this beam will do the job. And W, the letter tells us what the shape of the beam is. The first number tells us what the depth of the beam is, and the third piece of information is how much it weighs per unit of length. So in this case, because we're working in an imperial system, the W section, oddly enough, it doesn't refer to a W. The standard W section looks like this. It's an I. So this is a W section, right? It's probably the most common one that is used. Okay. So it's that shape. It is 27 inches deep, and it's 102 pounds per linear foot. Okay, so this 30-foot beam times 100 is, what is it? 3,000 pounds. So it's a ton and a half, that one piece, right? Obviously very heavy, needs lots of equipment to get it into place. So this discussion that goes on between the architects and engineers and the other engineers, we'll talk about more at another time, I think. But fundamentally, we know that the engineers want deep beams because deep is cheap, right? Just keep that phrase in your mind. Deeper is cheaper. Whereas architects want them to be shallow, right? We don't want depth because we need room to coordinate all the mechanical, electrical, and all the other stuff that has to go under the beams. And also we want lots of headroom in our usable space. So there's a bit of a struggle that goes on back and forth between the engineers and architects and the other engineers to coordinate all this. Okay, and that's so we see in this case we've got 18-inch beams here and here, and we've got some 27-inch beams, 27 inches deep here, and we've got even deeper ones on the perimeter, 30 inches deep along these two, because obviously this one is carrying these two, the load back to these two columns. Yeah. Okay, enough of the jokes about engineers. Okay. So architects, and what we also want is we want consistent depth, right? We don't want some of our beams deep and some of them shallow, because the engineers could design the system that way and come up with kind of an optimal amount of material. So that's the advantage of changing the weight per foot, because if we go back to, how do they do that? Well, if they want to add more weight to the beam and therefore more strength, they make it thicker, right? So you can just see in this, hang on, let me use my PowerPoint. You can see this okay?
Yeah, we can.
Yeah. Okay, so if we zoom in on this this wide flange beam over here, we can see that by adding additional thickness, they are varying the dimension a little bit, but in fact, what they normally do is they add the extra thickness to the inside so that the overall size of the beam, top to bottom, doesn't change. but the weight of the beam gets heavier because they've added more material on the flange here and more material on the flange there, which makes it heavier and stronger, right? It's able to carry more load. So the engineers will use a consistent depth and vary the weight of the member per foot to get the strength that they need. Yeah. So to the untrained eye, and again, this is why they need to put tags on the pieces of steel when they come to the site. You know, a 27 or a W18 by 40 looks much the same as a W18 by 30, right? And so we need tags. Okay. Shallow is mallow. Okay, there we go. Okay, any questions on that? All right. So this is a page from, I can't remember which text, the range of sizes that is available. And so we obviously need to know this information because we coordinate it into our drawings, right? And just like the structural engineers don't put plan and vertical dimensions on their drawings, and we don't put detailed dimensions of the steel members in our drawings. We show them in gray or in sort of very light line, and we make a note that it's there for coordination purposes only, that for the actual information about the piece of steel, they need to go back to the structural drawings, right? So we avoid conflicting information that way. And here's a couple of pages out of the structural steel handbook. And I'm not sure whether when you do your structures courses, what's her name? Why can I never remember her name? The structural engineer who teaches that course. I'm not sure how much detail she'll go into in this. Basically, the only information that we typically are concerned with as architects are the overall dimensions. All of this other data, the elastic properties, the modulus of deflection, and the plastic modulus, and what's the key one? It's been a while since I designed steel. Anyway, this gives the engineers the information they need to design. Okay, but as I say, the only thing that we're typically concerned with as architects are the overall dimension. Okay, any questions? So we know what we're building with. Now we need to put it up. And so here's an illustration of a building much like you're going to be working with this term. A single high bay building at the back of the building for warehousing or whatever. Concrete slab on grade. Steel columns, open web steel joists. The steel joists in this case are sitting on a trussed girder, right? So beams or trusses sit on beams or girders. And so these trusses are being carried by this beam, which is also a truss construction, back to this column and the load taken down into the foundation. In this case, we haven't spoken about these shapes yet, but they are sitting on what we call HSS, hollow structural sections. We'll talk more about those in a few minutes. So typical connection between open web steel joist sitting on a solid steel beam, the steel beam with a bolted connection to the column, right? In this case, a steel deck is sitting on the joist, and then concrete is poured into the steel deck to provide the final floor surface. So the connections, obviously, between the columns to the foundation are critical. All this load that we're bringing down from our 60, 80, 100-story building needs to be carried into the foundations.
Sorry, Professor.
And,
hello?
Question?
Yeah, sorry. Did you say the concrete was poured just directly onto the steel deck for the last image?
Yes. Well, I think did we talk about composite construction in lecture 1?
Maybe last semester. I don't know, but...
Maybe last semester. Okay, so in this case, we know that we can use the steel deck as formwork in effect, right? So it just gives a surface that the concrete can be poured onto, and the reinforcing goes into the concrete, and the steel fundamentally is not acting structurally. It's just a place to pour the concrete. Better is to get the two working together so that the steel goes into tension and does the work of the reinforcing steel. Yeah, and so that's done with what we call shear studs that induce composite action so that the concrete and steel are working together. The concrete is taking the compression, and the steel deck is taking the tension.
Okay.
Okay.
Yeah, thank you.
Okay. So it's called a composite action. To do with construction tolerances and also the ability to adjust these columns in the field, quite often we use a bolted connection like this, right? So that the base plate is welded or to the column, and then the base plate is supplied with, in this case, 4 holes at the corners, and sits on adjustable or is adjusted with nuts on bolts that are cast into the concrete. So these 4 nuts can be adjusted to get the column perfectly in position and perfectly straight. And then once it's in position, then the gap between the poured concrete and the steel is filled with what they call non-shrink grout, which is fundamentally a very, very strong cement water mixture, so that all of the load that's coming down in this column is transferred into the base plate, and the base plate is transferring the load through the grout into the concrete. And of course, the uplift, when we have our columns going into tension because they're being pushed sideways, then this bolt goes into tension and it takes that tension load down into the concrete, where the weight of the foundation will resist the overturning moment on the column. Yeah. Make sense?
Professor, sorry, quick one. For the assignment you gave us, if we give this kind of detail for some of the structure,
Yes.
of our structure, is this what you're expecting, or is it even more detailed than this?
Well, if you're lucky enough to have chosen a structure where you can see how the connection is made, then so much the better, and you can actually describe it in great detail. If it's concealed, so if you go back to this this situation here, I made a note. you remember we talked about control joints and cracking? When this, I'm trying to zoom in on there. You can see that when the concrete is poured, they haven't poured it right around the base of the column, right? So they do 1, 2, 3, 4 pours of slabs with control joints in between, and then at the end, after everything has been plumbed and straightened and adjusted, they can come back and pour concrete in that square around the base of the column. And so all you see at the end of the day in the building is this HSS, this square column disappearing into the concrete. But you know that underneath you've got this kind of situation. Yeah.
Okay, thank you.
All right. Right, and so we've had experience with putting casting steel anchor bolts into concrete. We used that in wood frame construction, right? So as a way of attaching the wood frame of a house onto its foundation wall, right? And we know that the purpose of those anchor bolts is to resist uplift, right? So that when the house is getting blown sideways, the windward side goes into tension and lifts up on those bolts. And so the bolts are cast deep into the concrete, and they are, there was the load of the, well, let's go to just a second. Just a second, I need to upload let's take a quick break for say 5 minutes. I need to upload something. I'll stop recording. You can go to the bathroom or whatever. I'm going to get myself a coffee, and we'll start again in 5 minutes, okay? So let's say 11:30, okay? Okay, you can hear me?
Yep.
Okay, so this is just a photo I found online showing the reinforcing steel that goes into the connection between a column reinforcing steel into the footing, right? So there's obviously a cage of steel, and it transfers that load eventually down to the bottom, and this is going to be filled with concrete to form the footing. So if we think about the logic of what we did in house construction, it's the same thing, right? So that we have, in this case, we've got a piece of steel cast into concrete, right? There's reinforcing steel in the concrete. This piece attaches to the plate of the bottom plate of the framing system, and therefore transmits tension into the footing, or the foundation wall, I should say, the foundation wall through its own weight. And also because of the weight of soil that is sitting on the footing, right? So all of the uplift that is trying to tip the house over, trying to pull it upwards, is also resisted by the weight of all this soil out here, which is sitting on, which is having a pressure on the footing. Yeah? That all makes sense? So the reinforcing steel that we just spoke about in the footing here is doing the same basic principle. Okay. And that's where we were. So we were talking about how with very big buildings, we've obviously got huge vertical forces to deal with, both up and down. Okay. Okay. Any questions? Okay. And so here is a good sized column coming into place. So this one is actually two standard so-called W sections. There's one, there's two, and they have been welded together by the use of a plate on this side and on this side, right? So they have created a huge column out of two W shapes, welded and probably welded all along this joint here as well. Yeah. So it's probably a ground floor column going into place for a very tall building. Yeah. And you can see that there's some plates that have been welded on at the next floor and the floor above that. So quite often the columns, if they can be transported through the city, you can imagine that these could be in the order of 45 or 50 feet long on the truck. And so obviously maneuvering them through tight city streets could be a problem. You may have to do it at night. And delivering these columns to site. And so, as I say, quite often they are continuous for 2 or 3 floors. And then there's a joint to the next column above. On the subject of those columns vertically, as the columns come down the building, they need to get bigger and heavier. The architects don't want them changing at every floor, so typically the engineers will do them in kind of banks of 10 floors or something like that. So the columns will be the same size for 10 floors, using the different weights the way we talked about a few minutes ago, and then they will change size for the next 10 floors. And so at least the architects know that they've got consistent dimensions on a kind of grouping basis. Erection of the steel by cranes, by either mobile cranes or tower cranes, right? Or jacking cranes or derricks. These are also, this particular shape is known as a derrick. And they can lift themselves up through the building as the building goes up. Yeah. So fastening techniques. We'll talk about a number of them. In this case, we're looking at a welder who is joining open web steel joists to a solid W section beam with welding on site. So the basics and a little bit of history. The progression was originally riveting and then bolting and now welding. Riveting is harder to do, and we'll talk more about why it is not used as much anymore. And now bolts are much more common because it is particularly with air pressure pneumatic wrenches, just like the ones you hear the mechanics using in the garage when they take the nuts off your car wheels. You can hear them using pneumatic wrenches. Same idea on site. They can be adjusted to provide just exactly the right amount of tightness or tension, right? Because as the nut gets tightened onto the bolt, what the bolt is doing is going into tension, right? And so you don't want to overstress it by tightening them too much. And then welding, typically welding done by electric arc welding, right? You see the guys out there with their masks on so that they don't blind themselves with the flash from the super hot welding process. And fundamentally what the weld is doing is making two pieces of steel one, because they are joining with steel in effect, or something that is stronger than steel. So riveting, obviously a very attractive, at least if you like that kind of aesthetic. Certainly the Victorian structures were very expressive and very kind of artistic in the way they used their rivets, I should say. And fundamentally what it is doing is it's taking a piece of metal, a plug, and then it's putting it through adjoining holes in the pieces that you need to put together, and then it is slammed with a riveting hammer or gun to deform the rivet enough that eventually it puts so much tension into this rivet that it is compressing these pieces of steel together. You know, how does it then work once you've got these three pieces of? So we have one piece here, we have one piece here that are the main structural shapes, and then we've got sort of a patch plate on both sides that are holding the rivets, and we can see those up here. So how is the stress being transmitted from this piece to this piece? You remember we talked about foundations, and we talked about piles, and we talked about the various ways that piles will transmit the load from a building into the earth. And there were various methods, right? Various transfer techniques that are used for piles. One of which is end bearing, right? So in other words, the weight of the pile, it just sits on something that's good and strong down there. And so the load comes down through the pile and it's transmitted off the end of the pile into the rock. Yeah? Another way is, do you remember we had something called skin friction piles? So if you remember, we had skin friction. And what does that mean? It means that for the length of the pile, it's transferring load all down its length due to the friction between the earth and the pile. Okay? Well, the same basic logic is happening here as well, right? So once you've compressed these, thanks to the rivet, which is pressing them super tightly together, the load from this piece through skin friction, some of it is going through the rivet itself. The rivet is obviously in shear, but some of it is also skin friction. So the size of the plate plays a part. And so skin friction from this into this and then back into this. Okay? And the same holds true for a bolted connection, which we'll talk about here, right? So here we see a worker with a pneumatic wrench tightening bolts on a very large column connection here, and various views of the same thing, right? So pneumatic torque wrenches give us the required tension. And it's interesting, you'll notice with this connection here that it's only the web of the beam that is connecting. We've got a space here and we've got a space down there. So all of the load is being transferred not through the flanges. So why are the flanges important in the structural behavior of this beam? Any thoughts? I get a little message here. Multiple users are typing. Yeah, the top flange is obviously important. Well, actually, it could be either top or bottom that the joists connect to. Yes, you could have some steel deck being carried on there too, which would provide the floor surface. But in terms of the behavior of the beam itself, the way it's transferring its load from the floor loads that are on it into the column. Yeah. The flanges are important for bending. You remember, we've got two fundamental forces that we're overcoming. We've got bending and shear, right? And we know that out in the middle of the beam, we have maximum bending, and at the column, we have maximum shear and zero bending, right? So the flanges really aren't, yes, we could use them to transfer some of the load, but really where it counts for all this shear that we're carrying is right here. So the web in this particular design has been left, the flanges have been left free, and the shear is carried through this web connection. Okay, so again, the idea, tighten up the bolts, induce skin friction between the adjacent pieces of steel, and Bob's your uncle, as they say. Okay. In this particular case, yes, the beams are at different levels. Don't know why, it's some peculiarity of the building. Don't know. And of course, some of these some of these bolts can be in place in the shop, and some of them have to be done in the field, right? So that a piece could be, the column could be shipped with this attachment plate already bolted on, and then the beams are bolted on in the field. Okay. So any special reason why they do what? The two beams at different levels? Is that what you're asking? It could be, for instance, that they may have a different floor structure here. I don't know. They might have, say, an access floor, or they might have, who knows, different floor levels. Will it affect the integrity? No. I mean, but the engineers obviously need to consider this because they're getting unbalanced force. This one over here looks high, this one's low, this one's high. So they're getting slightly eccentric forces coming onto the column there. Notice that they've also put in some transfer, what do we call these things? We talked about them last week. I can't remember the name on the top of it. It's on the tip of my tongue right now. Stiffeners, thank you. Yeah, web stiffeners, right? Or so these web stiffeners have been put into place to take care of perhaps the eccentricity of the loading. Yeah. So bolting, there's an exploded view. As I said, we could, for argument's sake, the column could come to the site with these two pieces already bolted on, and then the beam is bolted in the field. Okay. Different views. Oh, here we are. Shop installed and field installed. And these, those are typically in the shop drawings that are produced for the manufacturing of these, of all this steel. The shop drawings have notations that differentiate between a shop weld and a field weld, or shop bolting and a field bolting. You know? This one I was intrigued with. It's called a dog bone connection because it's got, you know, it's got a waist to it. And I thought perhaps one of the reasons was it made it easier for the for the workers sitting on there, like sitting on a horse, if they made the flanges a little bit narrower, it would make it easier to sit there and do the work of making the welds, etc. But apparently that's not it. But what some very smart engineers discovered is that by taking away some of the flange just before it connects to the column, that they get a stronger beam. Who knows why? But there's an article there that you can follow up and explore that one. So welding, the third technique, some of it may be done in the shop. We see that happening here. Lots of it will be done in the field. There's the welder's mask. There's the electric lines from the high voltage generator that is producing this super hot arc between the electrodes, and the welding taking place with eye protection. Yeah. So here's a typical notation about that would be put on the drawings by the steel fabricators. It would indicate whether this is to be done in the shop or in the field, and it would tell you the shape, the size, the strength, the depth, etc., of that weld. And so the different kinds of ways that we can join pieces of steel through welding are shown there. Yeah? We don't need to focus on that too much. But the basic chemistry is that the weld metal melts what they call the parent material. So the green zone is blue material which has melted. And so this is the weld metal going in. It's so hot, it's melting the steel on either side. And when it cools, it fundamentally is one piece of steel, right? So that the weld is capable of taking compression and tension as well as the native material itself. So we have, I mentioned earlier that we see a 2 or 3 story column come into place, and then we've got another 3-story column that goes on top of that, et cetera, all the way up the building. And so we have connections that we need to think about vertically, right? Sometimes we simply butt them end to end. Perhaps, as I mentioned before, the column at certain floor levels will change size, right? So it's because it's getting lighter as it goes up the building. We have a change in dimension, and therefore we've got a detail, something like that, or it could be something like that, right? With 2 base plates that are welded together, or sorry, 1 base plate, and then the next column is sitting on this base plate and bolted into position. So transfers vertically as the sizes decrease. Right, so steel decking, we talked about just briefly before. It comes in a whole host of different sizes, weights, thicknesses, and dimensions, and can be used for a variety of purposes. As the simplest one being simply as a metal deck that is not with concrete. We could use that on a roof. We put some protection boards on top of that, then some insulation, then some roofing, and we're done. It's a very lightweight construction. Or we could be using heavier sections and combine them, or be pouring concrete on top of them. And the third way is if we get what I mentioned before, composite metal decking. So the second one from the bottom, this one here, if you look very closely, You see these ridges along here. The concrete flows into these and transfers the tension forces from the slab into the steel. So in this case like that, there's also shear studs which are used, which I think I've got a slide of in a minute. But fundamentally what the purpose is to make sure that the concrete and steel are acting together, okay? Steel taking the tension, concrete taking the compression. There's another example of a shear stud being used. So in this case, the shear studs are they're welded right through the deck to attach the deck to the steel beam. And then we have concrete poured on top, and we have some reinforcing mesh. In this case, the reinforcing mesh is really to control cracking. It's not to act structurally, right? It's just very lightweight stuff, similar to what we put in a slab on grade. Any questions? There's some standard depths and profiles. Sometimes what we want to do is, for speed of construction, is use precast floor planks in combination with steel. You know? So obviously precast we'll talk about more later in the course, but fundamentally what it is it's concrete that is prefabricated in a factory, shipped to the site, and hoisted into position. And so we'll talk a lot about it in the precast concrete lecture. Just be aware that it's used together. I've got some photos just recently from they're building a new or rather extending a library at the University of Toronto, and they're using this technique. So I was taking some pictures there. Just some details of connections there. Okay, fireproofing. So we know that iron and steel do not burn, right? But on the other hand, when we subject them to fire, they get softer, right? And eventually, if they are soft enough, they start to lose their shape. They start to bend, yeah? And so once they've bent, then particularly the columns, if they go out of plumb, then all those properties that we looked at in the steel handbook of how they resist bending due to their shape, all that goes out the window and they collapse. So we have here is a part of the wreckage from one of the World Trade Center buildings when it collapsed. And of course, the steel didn't burn, but once it went out of plumb, it could no longer support the building. So we need to fireproof steel, and there's a number of different ways that we do it. Obviously, extremely critical in steel structures that we get the 2, 3, 4 hour rating that is needed. And what's illustrated here is gypsum board fireproofing. And these systems have been developed and tested in laboratories like UL and CSA and Warnock Hersey. And so they are rated systems, and you have to build them you have to build them exactly the way they are described. So the layer of drywall here between this piece of framing, a lightweight metal framing, and the structural seal. So we need a piece of drywall in there, and then we need 2 layers of drywall on the outside of this, and then we need to put the screws at certain spacings, and we need to put da-da-da-da-da-da. So the testing labs are very specific about the design. They give it a rating, and on we go. So we can simply call that rating up from one of the testing lab designs, put that notation on our drawings, and the building inspectors and the plan examiners issuing the permit know that we've achieved a rating of whatever. Yeah. So that's one technique. We can also, so a couple of comments in the chat box. Terracotta, yes, we'll talk about that in a minute. Does it apply to the exterior? I'm not sure what you're referring to. The exterior of the building? Do you mean a column that is on the outside wall, or a column that is totally exterior to the building? Well, if it's holding up the building, right? If the column is structurally necessary, then it has to have the same rating as all the others. Yes. Yeah. So the column, and so you're concerned about the gypsum board and weatherproofing, et cetera, et cetera. We'll talk about that in a minute and what some various techniques that are possible. I think what you're probably thinking about, and we'll talk about in a minute, is something called intumescent paint. That we'll see how that works in a second. So one of the common ones that is used is sprayed fireproofing. So here's the structural steel. In this case, it was only the beams that needed to be protected, not the deck. Different fire codes have different requirements. In this case, both the deck and the beams or the joists are being protected with the sprayed on fireproofing. This stuff is fundamentally cement-based, a lightweight cement, yeah? And that's what's providing the 1 or 2 hour or whatever rating you need. But the trouble with it is it's quite fragile, so it has to be protected from mechanical damage. You don't want things banging into it. So it is left exposed in some buildings, but quite often a ceiling is put in underneath it to protect it. And when they start attaching wires to hang the pipes or to hang the ducts or to hang the lights to these to this kind of protection, typically they will put the wire hangers in place before they spray on the fireproofing, because the process of attaching the wires tends to break off the fireproofing when it's done afterwards. Okay. Any questions? So sprayed fireproofing. It could be dirt, yeah. So sprayed fireproofing. I mentioned one here before, which we didn't really touch on. It's possible to use a hollow structural section, an HSS, and fill the column with water, right? So if you can make the thing absolutely watertight with a nice tight weld on the base plate, fill the thing up with water, and you've got a degree of fire protection. Yeah? All right, so coming back to Ron Eel's question about how do you expose columns? Well, here's our friend, the OCAD. Yeah, everybody's familiar with that building down at near the AGO on McCall Street. And what do we see? We see exposed steel columns, very colorful columns. And these are protected with what we call intumescent paint. Okay. And what this paint does fundamentally is when it's exposed to fire, it swells up. It turns into a a kind of fireproof foam. Okay. I used it years ago when it was just first being developed. We needed to protect, well, it was a university project. Yeah. There's a link here on the slides that will take you to describe this in more detail. And so obviously for visual purposes, architects like to use this intumescent paint. So here's intumescent paint on this beam, and here's sprayed fireproofing on that beam and on this column. And obviously, if you like the shape of your steel and you want to leave it exposed, then this paint is the answer. Okay. It needs to be maintained, of course. If it gets chipped or damaged in some way because of somebody banging their bicycle into it or who knows what, it needs to be touched up. But it works very well, and it's certainly now been accepted as a legitimate method of fireproofing. Here's a kind of blow up of what happens. Did we talk about wood and how? No, we haven't yet. About how wood chars, right? So we'll talk about that when we talk about heavy timber construction. When something burns, if it chars, it means that it develops a carbon layer, right? And what the paint does is produce a special kind of char that prevents the fire from getting, or the heat from getting through to attack or to soften the steel. It won't last forever, but it'll give you the 2 or 3 hours that you need to get the rating that you want, right? Basically, what we're looking for is enough time for the occupants to get out of the building and for the firefighters to get safely into the building and put out the fire. Okay. Laura's question about graffiti, good question. I don't think it has any effect, but a bonus marks if you can do a little research on that and come back to us with an answer. Whether or not graffiti has to be removed immediately, because you can well imagine that at art school somebody might be quite tempted to do something interesting with these colored pencils. Yeah. So intumescent paint, and I think we're getting close to the end here. So steel obviously is if the same as wood, in the sense that if we use a truss type construction, we can span the same distance with much less material, right? So here are some basic truss shapes and a detail of how they're connected. And just like with wood, instead of needing a great big heavy 2x12, if we make it out of lightweight members, but give the total span depth, right? Deep is cheap. We talked about that before. So in this case, deep is created by the depth of the truss. And so the truss can be made up of smaller pieces, smaller sections, and still achieve the same span and still achieve the same load carrying capacity, right? So steel trusses are used extensively, obviously in bridge work, large buildings, and we've talked about the advantages of trusses last week. Okay. All right. So we got through that. So let's go back to the agenda. Sorry, any questions on what we just did? Oops. Questions? Okay. No, that's not what I want. I want- Okay. So the group work on the steel project, we talked about that briefly at the beginning. I don't know whether anybody, if I go to the class count at the moment, we are now at 66. So there are more people here than were here at the beginning of the class. We talked briefly about the groups, how that was working, and the fact that some of the groups didn't seem to be able to communicate with each other. So you have until Friday to get make sure you've been in contact with your group and to get your proposal, if you haven't done it already, into the eCentennial Dropbox, which was created for that purpose. So let me have a look in those now. I said earlier, I haven't had a chance yet to go through them to review what you're proposing. So I see 22 of 26 groups have submitted. So whoever has not submitted, get your, they were due today. So I will go through those later today and give you feedback on those. I'm not sharing my screen, but I can. So this is the assignment folders for this course. And as I said, I'm seeing 22 of 26 groups have submitted. Okay. And only one member of the group has to submit, but make sure everybody's names are on it. Yeah.
Hello.
Yes.
Hi, sir. I have a question. Just because I'm having trouble contacting one of my group members because they're in a different section, and
Yes.
their name doesn't show up on the class list, so I have no way of emailing them or even getting a hold of them.
So when you go to your class list, you don't see the whole class?
No, I only see the people directly in my section, or at least that's how it was when I checked yesterday.
Okay, so you should see
Either that or the person that I was assigned with isn't
isn't
actually
registered
in
or
this
something.
class. Yeah, I'm
How
not
many,
sure.
when you go to your class list, how many people roughly do you see? I mean, look at what I'm seeing here.
Sorry, one second. Yeah, when I go to the class list,
Make sure at the bottom you've checked 200 per page, not
yeah.
the total users 131, including me.
Sorry, where do you see the number? Like,
Down at the very bottom. Do you see?
Mine is
oh, it says
65.
65, yeah.
Okay, so in other words,
So we're combined, but the class list doesn't show the combined list.
see what's happening. Okay, so what I will do is I will post an Excel sheet that has all this information on it, okay? And I will post that in, I'll do that. Well, I can do it right now. So let's grab all of this. Actually, there's a better way to do it. This way. Okay, so these funny green dots simply mean that that they are online at the moment. Okay.
Mhm.
Okay, so I'll attach this. I'll give this to you right now. Oops. Okay, so I just sent that to you in the chat box.
Mhm.
We'll also post it in this week's notes. Okay.
All right, and just the one other question. What are we supposed to do about people who simply just like don't respond to any of our emails?
Well,
Because I sent an email
yeah,
2-3 days ago, and just I didn't get any response. So I just kind of worked with the people that were there.
yes. And how
But
many?
like,
How many of your group are in that category?
there's 3 people who are responding, and the other 2 haven't said anything since we started the project. So
Okay. All right. Well, give them until Friday. Send. I'll send a note to the whole class.
Mhm.
And if they haven't heard by Friday, there'll be penalties involved. Okay.
Okay, thank you, sir.
All right. So you've got the list. Jihong, you can't see any of your group in the class list. Is that an old comment? Or is that, Jihong, are you looking at the spreadsheet? At the Excel file? Well, that's weird.
Yeah.
If you can't see your group members, I don't know what's going on. Which group are you in? Okay, so Jihong, I'm going to look here. You're in group 14. Okay. Okay. So these are your members, right, Jihong? So one way to do it is, which one can't you find? So if we take that student number and we look in here, we do a search on the basis of that number.
Sir?
Yeah.
If a group already submitted the proposal and they missed a student because they didn't have their student number, is it okay if we email you, or do you want us to resubmit it?
Don't worry about the student number. It's the name that's most important.
Okay.
Okay. That student number must be wrong because it's got too many digits. Let's try again. It's weird. They've all got. Do you people have 7-digit numbers or sorry, 9-digit numbers or not?
009.
Yeah, 9-digit.
And this one is
9.
Huh.
They have two numbers.
maybe they dropped the course. Weird that they would all be in one group, eh? You can't find any of them?
Oh, no. Well, I know I know some of those people, and I'm pretty sure they're still in the course.
Mind you, I've been having trouble with my search function in Excel for a while. So this person that we're looking for, there they are, Anna Carolina. So she's there, right? Ji Hong. Okay, so you've been in contact with them. Okay, well let's you and I talk offline. Okay, so after the end of the class, we'll see what we can figure out with your particular group. Anybody else having problems with their group? Okay, so let's put it this way. The class is finished, and I'm going to stop the recording. But the people who are saying you still have problems with your group, please stay online if you can. Do you have another class right away?
I don't have any class.
No. Okay, if you have to get going to something else, but if you can and you're having trouble with your groups, please stay online. I'm just going to stop the recording at this point, okay? And I'll see. So it doesn't sound. Sorry, just to finish up, it doesn't sound as though we have enough to do a practice class yet. So we will not have a practice class tomorrow. And we'll check. We'll see how we're doing for next week. Okay, depending on how fast you're moving through your design studio course. Okay, so I'll be in touch about that. Okay. All right. So I'll say goodbye to those who do not have a problem with their groups, and I'm stopping the recording. Yes, Mayhack, question. You want to turn your mic on? No mic? I see people are typing, but Mayhack, do you have a microphone? Can you turn it on and ask the question, please?
Hello.
Yes.
Actually, I want to ask, yesterday I saw something about model we have to make for our project. So what kind of model we have to make, from some cardboard or something?
No, it's more specific than that. Have a look at some of the examples from previous years, okay?
So where can we get that?
It's in the if you go to the content assignments. Here's one of the projects from another year. There's the site photographs, measurements, sketches, and there's a picture of the model. And the model is supposed to be sit on a base that's no bigger than 6 or 8 inches square, 150 to 200 millimeters. Okay, so they did a delightful, very little model here of the whole thing. If you're doing a larger structure, what sometimes I recommend is that you simply do one bay of the structure rather than trying to build the entire thing. If we look at this group here, their model is, they just did a model of one of the trees like that. You see? So people have used different materials. They've used metal. They've used wood, plastic, whatever they can, whatever they find most useful or most representative of the. I mean, the idea is to try and convey the essence of the structure that you're studying, right? And in their case, the essence of it was the lightness, the delicacy of this structure, right, in place. So that I thought that their model was able to do that quite nicely. It was light and kind of airy. And so these pieces here are just single thicknesses of paper. Does that answer your question?
Yeah, thank you so much.
Okay. Okay, so can we get back to the problem of communication with groups? I guess the first question then is, if somebody has dropped the course. So for that, I need to get the most current class lists. Yeah, that's right. The session will end shortly. Yeah, so if you highlighted, if you submitted your proposal and there's somebody in the group that's not been communicating, then please, you can take your submission back and just highlight anybody who's missing in action. If it's the majority of your group that is missing, or that you haven't been able to get in touch, I think you better send me an email, okay, about that situation. In the meantime, I will download what is the current class list as of today. And if somebody has dropped the course, then I will know that based on the current class list. All right? How does that sound? So, Kush, how do you...
Sir, I have a question. I couldn't find one of the members of my group the whole week, so I have already submitted the group sheet without that member's name. Is that a problem? Should I submit it again and highlight the member that I couldn't reach?
Yes, please do that.
Okay.
All right. So coming to Kush Buben, am I pronouncing your name at all correctly? So the scale is not a function. You do not have to produce it at any particular scale. What you have to do is to figure out how much of it you want to model in order to have it sit securely on an 8-inch base. or 6-inch base. Right? It has to be to scale for sure. If you need to adjust the scale to whatever, how much of whatever portion you're building. So the one that we looked at earlier, obviously they worked at a very different scale than these people. Yeah. Yeah, the base is 6 to 8 inches square. If 6 is the target, I'll let you stretch it to 8 if you really have to, but try and keep it 6. That's the way it's described in the assignment description, right? Is 3D printing allowed? That's a good question.
I want a 3D print.
Put it this, let's I would allow it if there's a particular reason for it. Yeah. I mean, I think that the assignment that I showed you a second ago of that little structure with the fabric roof, and they made it out of little metal, little pieces of metal tube, and it was delightful. Just a very sweet little model, and I still keep it in my office at the college. So there's really, no reason to work with a 3D printer. The purpose of this, part of the purpose of this exercise or assignment is to understand how materials go together, right? And so if you if you throw your hands in the air and say, okay, printer, you do it, you're not really learning about what the nature of how sticks of steel or sticks plus plates plus bolts, how it all really goes together. Yeah. Okay.
Professor?
Yes.
So I'm in the same group with Jack. It was 2 of us at first, but he said something about one of the other group members reaching out. They didn't participate in the group thing, but at least they're around, and we could probably get them to, I don't know, participate in further. But the other 2 we haven't been able to reach. But when I submitted the PDF, it was only my student number and his student number I was able to add. Do I need to submit it again with her student number, or is it okay if they just have their names on it?
Just names is fine.
Thank you.
Yeah. Any other questions?
Yeah, I just have one last question about dividing up the work.
Yes.
So because I know we might be going into quarantining again, and I know some people in the group might not want to come out, or they're not comfortable with leaving their houses.
Yeah.
So in terms of designing the model and having to go on site to draw do some drawings, how do we
I think
divide that up?
You need to discuss it amongst yourselves, and if you're all bound and determined to stay at home, but hopefully there's at least one person in your group who feels comfortable with putting a mask on and going out to do some photographs, some sketches, and some measurements. Hopefully 2 people, because it's always easier with 2 people to do measurements. So that's kind of my recommendation. And the people who really are determined not to leave home, then they get a different chunk of work to do.
Okay.
Yeah. And I leave it to you to explain or to discuss it and come up with a solution.
Okay.
All right.
Sir, I just want to paint a scenario that like I think is possible that could happen. If in it seems to me that most likely the person who handles the CAD of the structure, does the design, CAD design, is probably going to do also the 3D model. And in that kind of case, like
Why do you say that?
just because of other group projects that have happened, usually with the person that like so a lot of times maybe someone does the sketch or something or understands how the structure works. Is most likely that if you just delegate and say, okay, you do the CAD, you do the 3D model, the quality might not be one person. Let's say the person that does the CAD really knows what they're trying to do. The other person that does the model might come up with something that is not really great. Usually what will end up happening is maybe the person isn't satisfied with the what's it
Well,
called?
I think you can't just expect to. I mean, as a group manager, you can't just hand it to somebody and then not communicate thereafter, right? You have to have some back and forth, so the model maker can, to get together some materials and or make a proposal to you, the group, about how the model should be made.
Mm.
And the CAD drawer should have some intermediate issue drawings for the group to review and comment and improvements suggested, etc. So I think it's the individuals who are holding the pen, as it were, or holding the screwdriver to do the task, but it's the group that is commenting and guiding them. Yeah. So it's an exercise in group and team dynamics, and you've got things like MS Project to work with, and MS Project has a sketchboard feature, doesn't it, or a whiteboard to use for notes and ideas and things like that. Is that fair to say? Or Zoom?
I don't know MS Project, but there are ways to communicate with, I guess, like
I mean, you can even do, you can even do little hand sketches, right? And then, so I can do something like this, and then put my camera back on, and where's my camera? Do that, right? So there are many ways to communicate. Yeah.
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 Is your camera on? No, that's not.
I just turned it off again, but yeah. No, I just held up a silly little note here as a demonstration of the fact that there are many ways to do it, or we have well, we certainly in this program we have a whiteboard. I'm pretty sure we have it. You have it in other programs as well, right? The ability to mark something up, right? So that you can end up with a result.
Sir, I have a question. We have to wait for the approval of the proposal so we can start working, right, on the structure.
Yeah. And then you have till the end of October to finish.
Okay, thank you.
Okay. So we're getting a warning sign. We've got 3.5 minutes left in this session. And how are we doing? So, Jihong, if you can't contact it in my group, is it okay to submit on my own? No, it's too difficult to do all by yourself. So, excuse me, rather than doing something solo, I will put you into another group. I see. So you can select, yes, if your group is not responding, then go ahead and put in your proposal for what it is you want to do. Okay, get that approved by me or changed by me this week, and then you can move ahead. All right. Let's not give up on your group yet. Okay. Jihong, have you selected a structure? Okay. Well, why don't you do that? And let's start there and copy your group members. When you copy, send me an email with your proposal and copy your group members. Let's see what happens. Okay. 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 Well, we'll be in touch, and so first thing I've got to do is check to see if anybody has dropped the course, and we'll be in touch. How do we know if our example is acceptable? I will give you feedback. You know, using the feedback tool in eCentennial for an assignment. All right.
Okay.
Good stuff. Okay. Well, stay well, and we'll be in touch.
All right, bye, sir.
Bye-bye.